Imagine waking up to news that forces scientists to question the laws of physics themselves. That is exactly what happened on the 15th of March, 2026. Only hours earlier, the James Webb Space Telescope recorded a phenomenon so unlikely that its probability was calculated as 0% under any known natural model. This was not a minor anomaly or a statistical curiosity. According to the raw telescope data, an object known as 3I Atlas changed its physical behavior in a way that has never been observed in the history of astrophysics. In less than 40 minutes, what looked like an ordinary dark comet suddenly began acting like a perfect mirror floating through space. At 8:14 UTC, the object behaved exactly as astronomers expected. It was dark, rough, and absorbing almost all the sunlight that struck its surface. Nearly 96% of incoming light disappeared into it, the same way light vanishes into a piece of charcoal. To scientists observing from Earth, 3I Atlas looked like a typical cometary body, a mixture of dust, frozen gases, and carbon-rich material drifting silently through the vacuum of space. There was nothing unusual about it. Everything matched decades of models describing how comets behave. But then something changed. By 8:54 UTC, the reflectivity measurement, what physicists call albedo, suddenly spiked to 0.99. That number may sound small, but in astrophysics, it means something extraordinary. A reflectivity of 0.99 is not typical for rock, ice, or gas. It is the kind of value you would expect from a polished silver mirror or a flawless crystalline surface. In simple terms, the object had stopped absorbing light and began reflecting almost every photon that touched it. At first, scientists assumed the data had to be wrong. NASA's Deep Space Network flagged the reading as a sensor malfunction. Engineers restarted the telemetry systems. Instruments were recalibrated. Antennas were checked again and again. But when the system came back online, the readings remained exactly the same. An object nearly 180 million kilometers from Earth, traveling through space at 44 kilometers per second, had somehow transformed from a dark, light-absorbing body into a surface reflecting sunlight with astonishing precision. That alone would be enough to make headlines, but what truly disturbed scientists was something deeper. Nature does not polish surfaces in the vacuum of space. Natural objects develop rough textures, impact scars, dust layers, and chaotic structures. Asteroids are irregular. Comets release gas and debris. They do not suddenly reorganize themselves into near-perfect reflective geometries. Yet the raw data from Webb's NIRCam instrument showed something that looked less like a celestial object and more like an artificial beacon shining back the light of the Sunday. The obvious question was not just how it happened, but why. Physics does allow carbon to crystallize into diamond structures under extreme pressure. On Earth, diamonds form deep within planetary mantles, where temperatures exceed 2,000 degrees Fahrenheit and pressures reach hundreds of thousands of pounds per square inch. Even then, the process takes millions of years. But here, in the near absolute cold of space, roughly minus 270 degrees Celsius, the transformations seem to happen almost instantly. That alone would be astonishing. Yet the implications go even further. In physics, a perfect mirror in space is not merely a reflective object. Such a surface could act as a solar sail, a propulsion system powered by sunlight itself. It could serve as a shield, deflecting radiation. Under the right curvature, it could even focus energy with incredible intensity. 2 hours after this transformation began, something else happened that made scientists reconsider everything they thought they were observing. Because what appeared to be a simple crystallization event might not have been random at all. It looked increasingly like a deployment. To understand why this sudden shift in reflectivity is forcing scientists to rethink the rules of thermodynamics, we first need to look at what 3I Atlas was expected to do just one day earlier. Before the 14th of March 2026, every model predicted a completely ordinary cometary event. Astronomers expected dust clouds, water vapor jets, and a long glowing tail forming as sunlight warmed the frozen surface. Instead, the James Webb Telescope detected something very different, something closer to a phase transition than a cometary eruption. And what the telescope saw next was the moment scientists realized this might not be a natural phenomenon at all. At 8:42 UTC, the NIRCam instrument on the James Webb Space Telescope recorded a spectral signature that should never appear in the vacuum of space. Normally, when astronomers study a comet, the spectrum reveals a messy chemical mixture. Water, ice, methane, ammonia, and dust scatter light in chaotic patterns. That randomness is expected. It is the signature of a natural body formed through billions of years of collisions and chemical reactions. But the signal coming from 3I Atlas suddenly changed. The noisy spectrum vanished. The scattered chemical fingerprints disappeared. What remained was something shockingly simple, a clean, pure signal corresponding to crystalline carbon. In everyday language, the dirty mixture of frozen material covering the comet's surface had not merely melted or evaporated. It had reorganized itself into an ordered crystal structure. The transformation was so sudden and so perfect that NASA's scientists initially assumed the telescope must have miscalibrated itself. After all, according to the second law of thermodynamics, disorder in nature tends to increase over time. Entropy grows. Systems become more chaotic, not more organized. A comet spontaneously rearranging its atoms into a near-perfect crystal lattice would mean entropy had briefly reversed direction. But then the confirmations began arriving. First, the European Space Agency's Euclid mission, positioned at the same gravitational point in space, detected a 400% increase in brightness from the object in visible wavelengths. That measurement matched Webb's data. Then the ALMA radio telescope array in the Atacama Desert performed a radar reflection test. Instead of absorbing radio waves, like a dusty comet normally would, the object reflected them with the smooth precision of a polished metallic shield. 3 independent systems. 3 completely different detection methods. And yet they all reached the same conclusion. 3I Atlas was no longer absorbing radiation, it was reflecting it almost perfectly. To understand how extraordinary this is, consider what it takes to turn carbon into diamond. On Earth, diamonds form deep beneath planetary crusts where immense pressure squeezes carbon atoms into rigid lattice structures. The required pressure can exceed 725,000 pounds per square inch, combined with extreme temperatures that last for millions of years. But here was an object achieving something similar in zero gravity, at temperatures near absolute zero, and doing it in less than an hour. When researchers analyzed the data from ALMA more closely, they discovered something even stranger. The crystallization had not occurred randomly across the surface. Instead, it began at the equator of the object and spread gradually toward the poles. It moved like a wave. Imagine dropping a single ice crystal into supercooled water and watching the entire liquid freeze instantly. That is essentially what happened, except on a scale of kilometers across. This pattern suggested the process might have been triggered from inside the object itself. Natural comets do not possess internal mechanisms capable of aligning their atomic structures. They fracture, crumble, and evaporate. They do not organize themselves into precise geometric lattices. Yet by 9:15 UTC, The transformation was complete. The entire surface had become a 99.9% pure carbon lattice, smoother than almost any natural surface known in space. Measurements indicated a surface roughness of only 3 nanometers, which is smoother than the mirror used in the Hubble Space Telescope. Nature creates rough edges. Nature produces irregular shapes and chaotic fractures. But nature does not create a perfect geometric diamond sphere drifting through space, and the story was only beginning, because shortly after the crystallization ended, 3I, Atlas, stopped behaving like a normal celestial body entirely. At 10 UTC, astronomers noticed that the object's rotation, which had previously been random and unstable, suddenly stabilized. The tumbling stopped. The object aligned itself, and then the diamond surface slowly rotated until it faced directly toward the sunday. That behavior alone is enough to make astrophysicists uneasy. Rocks drift, asteroids tumble. They do not deliberately orient themselves toward a star with mathematical precision, yet the new rotational alignment of 3I, Atlas, placed its reflective surface within 0.01 degrees of the sun's direction. Statistically, the chance of that happening randomly is roughly 1 in 4.7 billion, which leaves scientists with two possibilities. Either we are witnessing a completely unknown physical process that rewrites the rules of material science, or 3I, Atlas, is performing a function. And what happened next, when sunlight struck that perfect mirror, may be the most unsettling part of the entire story. By 10:30 UTC, sunlight began striking the newly crystallized surface of 3I, Atlas, and that is when the physics of light itself suddenly became part of the story. In everyday life, we think of light as something weightless, something that simply illuminates objects without affecting them. But in physics, light carries momentum. Each photon behaves like a tiny particle capable of delivering a microscopic push when it strikes a surface. One photon alone does almost nothing, but trillions arriving every second can produce measurable force. Think of it like throwing ping-pong balls at a wall. One ball barely moves the wall at all. But if billions of ping-pong balls strike continuously, their combined impact begins to add up. Normally, when sunlight hits a dark asteroid, most of that energy is absorbed and converted into heat. The photons stop there. Their momentum transfers once and disappears into the material. But a perfect mirror behaves differently. When a photon hits a mirror, it does not stop. It bounces back. That means momentum is transferred twice, once when the photon arrives and once when it rebounds away. The result is double the push. This principle is the foundation of a propulsion concept scientists have dreamed about for decades, the solar sail. The moment 3I, Atlas turned into a near-perfect mirror with 99.9% reflectivity, the sunlight striking it began pushing harder than it ever could before. And according to NASA's telemetry, the object responded immediately. Instead of drifting through space as a passive body governed purely by gravity, 3I, Atlas began accelerating. Between 11 UTC and 12 UTC, its velocity increased by more than 4.2 kilometers per second. That may sound like a small number, but in orbital mechanics it is enormous. Objects do not casually gain speed like that without a powerful propulsion system, and yet there was no rocket plume, no chemical exhaust, no visible engine. The object was moving purely on the pressure of sunlight. In theoretical physics, that is exactly how a light sail works. Engineers have studied the concept for years, imagining ultra-thin reflective materials capable of riding sunlight the way ships ride ocean winds. If such technology could be perfected, spacecraft might travel to distant stars without carrying fuel. But the problem has always been materials. The sails must be extremely light, yet incredibly reflective. Our best experimental materials, thin films of mylar or graphene, tear, melt, or degrade under intense radiation. Yet here was 3I, Atlas, a massive body doing exactly what human engineering still struggles to achieve. It was literally riding the light of our own star. At first, scientists hoped the explanation might still be simple. Perhaps the object had accidentally formed a reflective surface, and sunlight was pushing it away from the sun in a straight line, like wind pushing a leaf. But at 12:45 UTC, the data revealed something far more unsettling. The diamond surface tilted by 14 degrees relative to the incoming sunlight. That detail changes everything. When you tilt a sail, you gain control. Sailboats on Earth use this principle to travel in directions that seem impossible relative to the wind. They can tack, adjust their angle, and steer across currents instead of simply drifting. And that is exactly what the trajectory data from the European Space Agency began to show. 3I, Atlas was not moving in a straight line. It was changing course. The object shifted onto a hyperbolic path that diverged from where gravity alone should have taken it. According to orbital models, the object should have been thousands of kilometers away from where it actually appeared. Astronomers call this type of motion non-gravitational acceleration. We have seen small hints of it before. In 2017, the interstellar object Oumuamua displayed a faint push that scientists believe may have come from evaporating gases. But the effect was subtle. What we were seeing now was not subtle. This looked less like a drifting rock and more like a controlled maneuver. Imagine watching a boat floating in the ocean. If it drifts with the current, that is natural. But if the boat suddenly raises a sail, turns its rudder, and begins cutting across the water, you immediately assume someone is steering it. And that thought is exactly what began keeping scientists awake. Because if 3I, Atlas, could adjust its orientation to steer using sunlight, then it was not simply a reflective object. It was navigating. But propulsion was only one piece of the puzzle. As scientists continued examining the spectral data, they discovered another property hidden inside that crystalline diamond lattice. The structure was not only reflective, it was dichroic. That means the material reflects certain wavelengths of light perfectly, while allowing others to pass through and become trapped inside the crystal structure itself. And that raised a question that made physicists deeply uncomfortable. Because in laser physics and fiber optic engineering, diamond lattices are sometimes used to trap and amplify light internally, which leads to a disturbing possibility. Was 3I, Atlas, simply using sunlight as propulsion, or was it storing that energy for something else? At 13:15 UTC, the data produced a new mystery that pushed the situation from strange to deeply unsettling. As sunlight continued striking the reflective surface of 3I, Atlas, scientists expected the object's temperature to rise. Even the most reflective surface still absorbs a small portion of incoming radiation, and over time, that absorbed energy should appear as heat. But the temperature readings did the opposite. They dropped. The internal temperature of the object began decreasing even while it was being blasted by intense solar radiation. Under normal thermodynamic rules, that should be impossible. Energy cannot simply disappear. If sunlight is not becoming heat and not being fully reflected away, then it must be going somewhere else. Researchers began calculating the missing energy. The result was staggering. Roughly 400 gigawatts of power appeared to be vanishing into the crystal structure every second. To put that into perspective, that is roughly the combined electrical output of 200 Hoover dams disappearing into the object continuously. Where was that energy going? One theoretical explanation comes from a concept proposed decades ago by mathematician John von Neumann. He described the idea of a self-replicating probe, a machine capable of traveling between star systems, gathering resources, repairing itself, and continuing its mission indefinitely. At first, astronomers believed 3I, Atlas, was a simple rock. Then they thought it might be a comet. After the crystallization event, it resembled a mirror. But by 1340 UTC, some scientists began considering an entirely different possibility. What if the object was acting like a capacitor, a structure designed to store vast amounts of energy? That possibility leads directly to another. If you have a perfect mirror capable of reflecting light, and you have a structure capable of storing enormous energy, then you also possess the ingredients for something else entirely. A focusing system. When mirrors are curved into parabolic shapes, they do not simply reflect light. They concentrate it into a single point. The ancient Greek mathematician Archimedes is famously said to have used mirrors to focus sunlight onto Roman ships during the siege of Syracuse. Whether that story is entirely accurate or not, the physics behind it is real. And at 1430 UTC, something happened that made this ancient idea suddenly relevant again. The flat mirror surface of 3I, Atlas, began to curve. Telemetry suggested the once smooth, reflective face was subtly changing geometry until it formed a parabolic dish. Instead of reflecting sunlight broadly, the object appeared to be focusing it. Even more alarming was the direction. The dish was not pointed toward Earth. It was aimed at a very specific location, deep within the solar system. That location was Saturn. More precisely, it was pointing toward Enceladus, one of Saturn's icy moons. Enceladus has fascinated scientists for years because beneath its frozen crust lies a global ocean of liquid water. Jets of water vapor erupt from cracks in the surface, carrying complex organic molecules into space. Many astrobiologists consider it the most promising place to search for life in our solar system. At 15 UTC, the focused sunlight from 3I Atlas reached its target. A coherent beam of light struck the south polar region of Enceladus. The effect was immediate. Normally, the moon's geysers release about 200 kilograms of water vapor per second, but after the beam arrived, the plume activity surged dramatically. Instruments detected a sudden eruption, ejecting tens of thousands of tons of material into space. This was not a random flash of reflected light. The beam behaved like a laser powered by sunlight, and the probability that a natural asteroid would accidentally focus energy onto the exact location where organic chemistry is most active on Enceladus is essentially zero. If this event has a natural explanation, it has not yet been discovered. But if the object is some form of probe, the implication is extraordinary. It may not be attacking anything. It may be drilling. And that possibility raises a question scientists cannot ignore. If 3I Atlas can concentrate sunlight into a beam powerful enough to melt ice on a distant moon, what happens if it ever turns that beam toward a planet with an atmosphere? At 1530 UTC, the beam suddenly stopped. The parabolic surface of 3I Atlas flattened again, returning to the perfect mirror-like geometry it had shown earlier. At first glance, it seemed like the event had ended, but when researchers began comparing the data with historical observations of Enceladus, they noticed something unsettling. The fractures on the moon's surface, the long cracks scientists call tiger stripes, align suspiciously well with past solar anomalies recorded over extremely long timescales. These fractures are the same regions that constantly eject water vapor and organic molecules into space. When scientists mapped those locations against patterns of unusual solar energy spikes recorded in astronomical archives. The alignment looked far too precise to be coincidence. That possibility leads to a chilling idea. What if 3I, Atlas, is not unique? What if objects like this have visited the Saturn system before, repeating the same process over millions of years? If that is true, the beam we witnessed might not be an isolated event. It could be part of a recurring maintenance cycle, something periodically interacting with Enceladus beneath the frozen crust. And then another discovery complicated the situation even further. When astronomers at the Keck Observatory in Hawaii analyzed the light spectrum of the beam, they found something that should never appear in ordinary sunlight. Embedded within the focused energy were spectral lines belonging to technetium. Technetium is an unusual element. It has no stable isotopes and does not naturally persist for long periods of time. Its half-life is roughly 4.2 million years, which is incredibly short on cosmic timescales. If technetium appears in a signal, it means the element was created relatively recently. In most cases, technetium is associated with nuclear reactions. That means the beam from 3I, Atlas, was not simply reflecting sunlight. It was modifying the light itself. The mirror-like lattice appeared to be encoding additional information or energy into the beam before sending it toward Enceladus. And when the beam reached the moon, something remarkable happened. At 16 UTC, the chemical composition of Enceladus's plumes changed dramatically. Measurements showed the concentration of complex organic molecules increased by nearly 800%. The moon did not simply melt ice and release water vapor. Its chemistry shifted in response to the energy input. For scientists studying astrobiology, that observation is impossible to ignore. Geological processes can release water and simple molecules, but the rapid change in complex organic ratios suggests something more active. This begins to look less like geology and more like chemistry, possibly even biology, which raises an unsettling question. If 3I, Atlas, is deliberately stimulating the organic environment beneath Enceladus's crust, what exactly is it trying to accomplish? One theory suggests a Gardner scenario. In that interpretation, the object could be part of an ancient system designed to encourage the development of life. The beam might provide energy, trigger chemical reactions, or accelerate biological processes within subsurface oceans. But there is another possibility. The beam may not have been encouraging life at all. It may have been analyzing it. If the object is collecting data from Enceladus's organic plumes, then the entire event might represent a form of biological sampling on a planetary scale. And if that is true, then someone or something might be observing the results. Because shortly after the plume composition changed, global communication networks recorded an unusual development here on Earth. The European Space Agency suddenly went silent for 4 hours, and an emergency meeting was quietly scheduled involving multiple international space agencies. Something about the data had triggered a deeper level of concern, and what happened next explains why. At 16:15 UTC, only minutes after the plume composition spike on Enceladus, 3I, Atlas rotated again. Until this point, every observation could still be interpreted cautiously. Scientists had confirmed 4 key facts. First, the object had transformed from a dark comet into a 99.9% reflective diamond-like lattice in less than 40 minutes. Second, it used solar radiation pressure to alter its trajectory, effectively steering through space using sunlight. Third, it focused a massive 400 gigawatt beam directly onto the organic-rich plumes of Enceladus. And fourth, the beam contained technetium, a clear marker associated with nuclear activity. These are not speculative theories. They are documented observations from multiple independent instruments operated by NASA, the European Space Agency, and ground-based observatories. But one question remained unanswered, and it is the question that forced an emergency closed-door briefing at the United Nations only hours ago. Why did the beam contain technetium? Because technetium cannot survive for billions of years in space. Its relatively short half-life means it must have been created recently. That leads to only two realistic possibilities. Either the element was synthesized somewhere else and recently added to the beam, or it was generated inside the object itself. And that distinction changes everything. If 3I, Atlas, is an artificial probe, then it is not merely observing the solar system, it is interacting with it, possibly influencing the chemical environment of worlds like Enceladus. In the Gardner interpretation, the beam might be part of a process designed to trigger or accelerate biological evolution on icy moons. Such a machine would effectively act as a panspermia engine, spreading or nurturing life across star systems. But there is another scenario that scientists cannot ignore. If the beam was not stimulating life, but instead extracting information, then the object might be performing a survey, analyzing biological environments, the way researchers on Earth sample soil or ocean water. And if that is the case, the data collected may already have been transmitted somewhere beyond our solar system. While those debates were unfolding, astronomers continued monitoring the object. At 1645 UTC, 3I, Atlas completed another rotation. It turned away from Saturn. The parabolic mirror flattened again. The object stabilized its axis once more. But this time, the reflective surface did something different. The diamond face slowly rotated until it pointed directly toward Earth. At first, scientists assumed the mirror would reflect sunlight toward us the same way it had directed energy toward Enceladus. But the instruments reported something unexpected. The albedo dropped to zero. The brilliant mirror surface that had reflected nearly all incoming light suddenly became a black body, absorbing radiation instead of reflecting it. The object was no longer transmitting energy outward. It was collecting signals. In other words, for the first time since the transformation event began, 3I Atlas appears to be listening. Listening to what, exactly, remains completely unknown. It could be scanning our planet's electromagnetic noise. It might be analyzing radio transmissions, radar signals, or something else entirely. Whatever the purpose, one fact is clear. The object has shifted from interacting with a distant moon to orienting itself toward Earth. And that is where the story stands right now. A mysterious object has rewritten the rules of astrophysics, steered itself through sunlight, focused immense energy on a potential ocean world, and finally turned its attention toward our planet. The next data update from global observatories could arrive at any moment, and whatever it reveals may change how humanity understands its place in the universe. If you want to stay updated on this unfolding cosmic mystery and explore the most fascinating discoveries happening across our universe, make sure to like this video, subscribe to the channel, and share your thoughts below. Because the story of 3I Atlas might only be just beginning.